So here's how I like to develop a lattice. Notice this is a non-recombining lattice. RUD and RDU will be different. And that tends to be the case in interest rate lattices, that they're non-recombining, unlike the stock lattices, which do combine. So here we have time 0, time 1, time 2, time 3. And the formula we just saw for the expected value of the price of 0,3 is a risk-neutral expected value of all possibilities of the form E, all possibilities of the form e to the minus h times the sum of rates in between time 0 and time 3. And so if we simply look at the combinations, how many different sets of rates can we achieve going from time 0 to time 3? And the answer is we always start off with 1, and then we have a choice in the next period of either RU or RD. And then in the next period we have a choice. This is the way in which I like to use this lattice notation, because it helps us think through the combination of paths. Namely, that in this summation there are 4 sets of 3 rates in the summation. There's R, RU, RUU, R, RU, RUD, and similarly for the other 4. And that's precisely what we just saw in this formula. We have the R, RU, RUU. Then we have R, RU, RUD, and the other combinations. And this pattern generalizes, no matter how many steps I have in my lattice, the formula that the price of a 0 is the risk-neutral expectation of this summation is always true. What gets to be more complicated is the combinatorics associated with writing down all possible combinations of these interest rates. So if I have an n-period lattice, I have a choice of 1 rate for the first period. I have a choice of 2 rates for the second period. I have a choice of 4 rates for the third period, and so forth. All the way to the final period would be, this would be, so this is a 2-period lattice, so it would be 2 to the n. It's quite a few combinations. As n gets big, the number of steps in the lattice get big, one generates more and more, if you want to reflect all possible combinations of n period rates in the lattice. It gets quite sizable in terms of how many combinations there are, and this is what motivates sampling. And this is what motivates the Cox-Ingersoll-Ross result, that being that instead of generating all possible combination of interest rates, you generate them stochastically. You do a sampling of 1,000 curves, say, and you do this average based on the sampling of 1,000 curves. To get the exact answer according to this lattice, you would need to reflect every combination of interest rates, of which in an n-step lattice you can see it's a pretty big number. And in particular, this would be 2 to the n times n plus 1 over 2. I think that's right, because I'm adding exponents from 0 to n. Maybe it's that plus 1. Right, but I'm just adding the exponents of 2. So it's a pretty big number when n gets big, and there's a lot of work here to do this lattice accurately. So first of all, note that one can generate, using the Cox-Ingersoll-Ross approach, a price explicitly in terms of a risk-neutral probability of all possible combinations. And that's easy to do. Now notice that when you do this expectation, you need probabilities for each one of these paths. These 4 paths in this example are not equally likely. Indeed, we see from the prior that the probability of this upper path is p squared. The probability of the lowest path is 1 minus p squared, and the intermediate paths have the same probability. Well, the probabilities in general depend on how many up versus down states one has. And we won't go into the combinatorics.